Okay, this is Notes 5.2 Part 2, Valence electrons. Valence electrons determine how atoms bond and react. We can use the periodic table to determine the number of valence electrons in an atom. Lewis dot structures are used to represent the valence electrons available for bonding. For each element shown, write the short form electron configuration and the number of valence electrons. Then below the periodic table, write the charge of the typical ion that is formed by elements in that family. Sorry, right there. That's what I just read from. Okay. All right, I'm going to make this real easy for you. Let's count carbon's valence electrons. 1, 2, 3, 4, 4. Now check this out. Let's see what row or what column carbon is in. 1, 2, 3, 4. Whoa. How about that, huh? I wonder if the same will work for oxygen. Let's see. 1, 2, 3, 4, 5, 6. Check it out. 1, 2, 3, 4, 5, 6. Let's do fluorine. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So basically you can use the periodic table to figure out how many valence electrons are in an atom. Okay, if I start over here, I count this row, I count that row, column. I count this column, that column. I skip the transition metals. I go over to my P block. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. That model will work for a lot of these elements. For the important ones that we're worried about, it works. It doesn't work for all of them, but it works for most of them. So the number of valence electrons here, okay, for hydrogen, 1 valence electron. Same thing here, 1 valence electron and 1 valence electron. Okay, well, how about beryllium and magnesium? 2 valence electrons. I'm going to fill this out. You do the same, and when I come back, you can check your answers against mine. Okay, check your answers. Make sure that you got them right. 1, 2, 3, 4, 5, 6, 7, 8. With the exception of this guy right there, helium. Because helium only has 2 electrons total, okay? And that first row, remember the first row only has 2 seats, so helium's the only exception. It's got 2 valence electrons, okay? All right, so how about, let's look at fluorine. I mentioned it in the video before, and we watched the video on fluorine, hopefully. Check it out. Fluorine really wants to fill that last seat, doesn't it? Well, if that's the case, then when it forms a charge, it's going to form what kind of a charge? A -1 charge. Okay. What about oxygen? Oxygen has 6 valence electrons. Oxygen has 6 valence electrons. That means it's got 2 empty seats that it really wants to fill. So once it does, it will form a -2 ion, or a -2 charge. Nitrogen we haven't done, but it's got 5 valence electrons, which means it wants 3 additional electrons. Okay? And whenever that happens, it gets a -3 charge. Now look at this number between 4, what I'm trying to say is this: 4 falls right in the middle, doesn't it? of the number 8, between 1 and 3 and 5 and 8. Okay, it falls right in the middle. So this will not gain nor lose. These guys do not gain nor lose electrons. They do not form charges readily. Boron, however, has 3 valence electrons. It's a lot easier to lose those 3 valence electrons than it is to gain 5. It's easier to give those 3 away, so it will form a +3 charge. Now these metals here really like to lose electrons because they've only got 2 in their outer shells. Do I have any metals? Did we do a metal? We did magnesium, I think, didn't we? Let's look at that. Okay. So in magnesium's case, it's way, way easier. It takes less energy just to get rid of these electrons than it does to try to fill up 6 empty seats. Are you kidding me? It takes a lot less energy to just give those away. So magnesium will form a +2 charge. And these guys over here, well, they have only 1 valence electron, so you can imagine that they really, really want to give them away, and they form a +1 charge. Okay, that's how that works. So these are how the charges work. Remember, the noble gases, they have their outer rows full, so they don't react. Okay, they don't react. Now, it said in the notes to do your short form configurations here. Maybe we can do 1 or 2 of them. Let me see how much time. Yeah, we can do, well, actually, I'm just going to post them here. You can write in your short forms, all right? And I'm going to post them here and pause it so you can have a look. Okay, there's your short form configurations. Let me zoom in a little bit. Okay. And I will pause right there so you can see. Let me focus. Okay, explain how an element's position on the periodic table can be used to predict the number of its valence electrons. Well, S and P block elements have similar, let's just say this, the number of electrons in each family is the same because they have similar short form electron configurations. The number of valence electrons increases from 1 to 8 going from left to right, excluding the transition metals. So valence electrons increase from left to right. And it's real important to say excluding the transition metals. Okay. So as we go from left to right, the valence electrons, the number of valence electrons increases by 1. With the exception of the transition metals, we skipped them, right? They would be right here. Describe the pattern of the charge of typical ions formed by the element. So why is this pattern observed? Okay. Non-metals, let me do it like this. Non-metals in groups 15, 16, 17 gain electrons to fill their outer seats, where metals, let's just say atoms, now let's say metals in groups 1, 2, and 13 lose electrons. Okay, they lose the electrons like we said earlier. Those metals want to give them away. It's easier to give them away than to try to gain electrons for them. So let's go ahead and do the electron configuration for barium, tellurium, and cadmium. We'll figure out their Oh, okay, then we'll do their ions. Okay, so for barium, barium's Ba. Where did it go? Barium, Ba. Okay, it's all the way down here. You know what? Let me do this. This is going to go long if we do this. So let me go ahead and start a new video here.